Hi, welcome to the dynamics tutorials. So we're going to solve another problem with work and energy, but we're also going to have to do a little bit of work with the equations of motion on this problem, and this is also a kinetics problem. So we have a small car here that begins with a toy car that begins with an initial velocity at A. It has a mass of 0.5 kilograms. It goes around the loop. Point B here is at the top of the loop. The radius of the loop is 0.250 meters, so the loop is circular. After the loop, it goes down this little drop of 0.2 meters, and then it contacts a spring, which is initially unstretched and uncompressed, and then it compresses the spring until it stops momentarily, and that's at point C. We have a spring constant of 200 Newton per meter. So we want to find out how fast does the car have to go at A in order to not fall off of the track at B, and then if it's going that minimum speed, then how far does the spring compress at C. So we can draw the free body diagram of the car at B. So at the limit of leaving the track, the normal force from the track at that point would be 0. So we really would just have the weight of 0.5 kilograms times 9.81 meters per second squared. We can plug that into a sum of forces in the normal direction is equal to mass times acceleration in the normal, and that acceleration in the normal is going to be v squared divided by the radius of curvature. So the weight is equal to the mass times vb squared divided by the radius of curvature. Don't forget to take your square root here, and that gives you a VB of about 1.57. Then we can plug this into a work and energy equation here. So the initial kinetic energy plus the work done on the particle from position 1 to position 2 equals the final kinetic energy. So our kinetic energy is just 1/2 mv squared. And then the only thing that we have doing work is the change in elevation on the car. So we're going up 2 radii, so it would be the weight times the 0.5 meters height of double the 0.25, and then that's equal to the final 1/2 mv squared term. Oops, I left off the square there. So then you can solve this for VA. Don't forget again to take your square root since velocity squared, and you'll get a VA of 3.5 meters per second. Then we'll look at it going from A to C. It doesn't really matter what happened in between those because we're assuming that there's no frictional losses. And so we can set up another work and energy equation. So we have its initial kinetic energy, and then we have the drop from in 0.2 meters doing work on the car, and then we have the spring being compressed taking work out of the system, and then that leaves us with our final velocity. So we'll plug in our velocity, our mass, and then our velocity at point A that we just solved for. We'll plug in the weight, it's 0.5 times 9.81 times the drop in elevation, so it's going to be a negative 0.2 meters. And then we'll plug in the minus 1/2, so this is this term here, 1/2 the spring constant, 200 Newton per meter, times the S2 squared. The initial stretch in the spring was 0, so that second part is 0. And then the final kinetic energy is 0 because the car has stopped. And we can solve for S2. Again, don't forget to take your square root, and you'll get S2 is 0.201 meters. Thanks for watching.